In this video, we look at binomial distributions. In order to understand binomial distributions, we need to understand what Bernoulli trials are. So Bernoulli trials are just repeated trials that are identical and independent. The identical part means that every part of the experiment is the same, and the independent means that every time we perform the experiment, the outcome of the previous trial does not impact the outcome of the next trial. So, for example, flipping a coin to see how many heads we can get. That would be a Bernoulli trial. We're repeating a whole bunch of times. Every time we flip a coin, the experiment's exactly the same. And the results of the second flip, third flip, and so on don't depend on what happened the first time through. Every time we flip the coin, we still have a 50% chance of getting ahead. Now, the other part of a Bernoulli trial is that there are only two possible outcomes. We either have success or failure. So in the example of flipping and counting the number of heads, all of the heads would be successes and the tails would be failures. We can still have Bernoulli trials if we talk about, say, rolling a die and trying to get a 6. In that case, a success is getting a 6 and a failure is getting anything else, a 1, a 2, 3, 4, or 5. So for binomial distributions, the random variable is the number of successes in a given number of trials. We'll work through an example so you can see what that looks like. So here's a question, an example. Basically says that there's a 70% chance that an allergy drug is effective for somebody with the symptoms that the drug treats. Question's asking, what is the probability that out of 10 random people, the drug is effective on 6 people? So in order to do this, we have to look at a whole bunch of different cases. So I'm going to start with case number 1. Case number 1 is going to be the case where the first 6 people have success. So case 1. For our first person, there's a 70% chance of success. Our second person has a 70% chance of success, and this continues on. And because we're looking for 6 successes, we're going to do 6 of these. Now, if those are successes, then everybody else must fail, so the medication is not working or does not treat the symptoms. So there's a 30% chance for each of those failures. So we take because we have all of the successes and all of the failures, we take all of the successes, multiply them together, and take all of the failures and multiply them together as well. So that's just one situation, though, where all of the successes came first and all of the failures come later. And I just realized that I'm missing I've got an extra 0.7 in here because I only have 3 blanks. So let's add one more blank in here. We'll add one more. So case 2 might be this case right here, where most of the successes come at the beginning. So 1, 2, 3, 4, 5 of them come at the beginning, and one comes a little bit further on. Well, again, there's a 0.3 chance of failure for these failures. So we can put a 0.3 in there. Now notice for both of these cases, there are 6 0.7s multiplied together and 4 0.3s multiplied together. So it's looking like our probability is going to have 0.7 to the exponent 6, because there are 6 of them in there, and 0.3 to the exponent 4, because there are 4 of those. Now, what we really need to do is to figure out how many ways can we have, how many of these different cases. Obviously, there are 2 cases here, but there are a whole lot more cases. And in fact, in order to figure out how many cases there are, what we want to do is we want to look at how many ways are there to choose 6 people from 10 for whom the drug will be effective. Well, that's just equal to 10 choose 6. So there are 10 choose 6 ways to choose those 6 successes. Then we multiply that by the probability of success to the exponent of the number of successes that we have. And we multiply that by the probability of failure to the number of failures that we have. So we can plug that into the calculator. 10 choose 6 is 210. So there are 210 cases. You can see why we wouldn't want to go and list all of them. So we get 210 times 0.7 to the 6 times 0.3 to the 4. And again, if we multiply that all out, we should get 0.20, which means that there's a 20% chance that 6 out of 10 people are going to be have success. So what is the probability that out of 10 random people it's going to be effective on 6? Well, it's a 20% chance. So therefore, there's a 20% chance that 6 people, that the drug will be effective for 6 people. So you get the idea here that the drug will be effective, works for 6 people. So that's how we can actually go ahead and do this question. You can see here that we're using a little bit of probability. Obviously, it's a probability-related question. We're also using some information here with combinations. And it turns out that for all Bernoulli trials, for all binomial distributions, which are Bernoulli trials, that idea is always true. So the formula here for calculating the probability is just this. So this is the probability that our random variable x is equal to any one of the given values. In the previous example, we just said what's the probability of getting a 7 or having 7 successes. But we could have written that as what's the probability that our random variable, which was the number of people that the drug was effective for, was equal to 7. So that's 2 ways to write the same thing here. We should talk about this a little bit. Obviously, this looks very familiar to what we just did. N here is the number of trials. Maybe we'll try to jot that down in here. So this is the number of trials. Remember, these trials are independent. R is the number of successes. So in our case, we are looking for 6 successes. So these are the successes. That's actually the number of successes. Now, P in this case was the probability of success. So the probability of having a success. So in our case, the success was that the medication was effective. The probability of that success was 0.7, so P was 0.7. So this is the probability of success. And Q is the probability of failure. So in the example that we did, Q was 0.3. That was a 30% chance that the medication wasn't going to work. So this is the probability of failure. And we've already defined N for the equation here. This is the number of trials, and this is the number of successes. Another way to put this, N minus R is just the number of failures. So the number of failures. There's a lot to unpack in this. Once you go through it a few times, you start to get the hang of it. Let's do an example so we can see it all together in action. So here's the example. We have a pair of dice. I should say a pair of dice, not a paradise, but a pair of dice. They're rolled 10 times, and we're going to calculate the probability that double sixes are rolled twice. So really what this question's asking for is asking for what is the probability that our random variable, maybe we should define our random variable first. I'll just do that up over here. So let x, our random variable, represent the number of sixes. So the probability that x is equal to 2, this is our capital X, our random variable, is just equal to, and we're going to use the formula up here, N is the number of trials. Well, we're rolling the dice 10 times, so that's N. And actually, maybe it's not a bad thing to list off to the side what the different parts are. So N is the number of trials. It's equal to 10. The probability of success. Oh, hang on. We need R. Let's do R first. R is the number of successes. We want 2 successes, so R is going to be 2. The probability of success is the probability of getting double sixes. So the probability of getting double sixes is just equal to, what is the probability of double sixes? There's only one way to get double sixes out of 36. So the probability of success is 1 out of 36. And the probability of failure is 1 minus that, or just the number of outcomes when you roll 2 dice and you don't get double sixes. It's 35 out of 36. So now we can fill these into our equation. We need an N choose R, so 10 choose 2 times the probability of success. P is 1 over 36. The exponent here is the number of successes. So if you look here, R is the number, it's the same as this value, the number of successes. So R is 2, we want 2 successes, and then we're going to have 35 out of 36, and this is the number of failures. Well, for doing the experiment 10 times, and 2 are successes, how many failures will there be? Yeah, 8 of them will be failures. So we get an equation that looks sort of like this. And we get, pardon me, so 10 choose 2 works out to 45. And then we could either work this out as a fraction or a decimal. In the long run, we're going to go for a decimal anyway, so we may as well convert this to a fraction. So 1/36 is just equal to 0.028, we'll say. 0.27 repeated, so we'll call that 0.28. That's going to be squared. And then if we do 35 out of 36, we get 0.972 to the 8. And then so now we can just multiply this all together and see what we get. So we'll do 45 times 0.028 squared times 0.972 to the 8, and we get approximately 0.03. Oh, sorry, I got my 3 in the wrong spot. Let's fix that up. So 0.03 by the looks of it. So that's the probability that we're going to get exactly 2 double sixes when we roll the dice 10 times. So approximately 3% chance of getting double sixes exactly twice. Now the next question is a little bit different. I may not have room to do all of it, but we can get started on it at least. Maybe we can find some room on the side. The question here, very similar, but it says, what is the probability that double sixes are rolled at least twice? So at least twice, we want to know the probability that x equals 2 plus the probability that x equals 3 plus the probability, and so on until we get to the probability that we get 10 sets of double sixes when we roll. Oops, sorry, not 6, but 10. Now, that's a lot of calculations. There must be a faster way, and the faster way is the indirect method, which is saying that that's just equal. So the probability that x is at least 2 sets, so x is at least 2, that's greater than or equal to 2, is just going to equal 1, the total probability, minus the probability that there are no double sixes, so the probability that x equals 0, and minus the probability that x equals 1 set of double sixes. Here's where I start to run out of room, I think. So let's have a look here. We can set this up. The probability that x equals 0, we're just going to use our formula from way up at the top here. Formula from up here. We need n. So n is still 10. So we're going to do 10, choose 0 this time. Probability of success is still 1 out of 36. And the probability of failure is still 35 out of 36. Now, for this trial, we have 0 successes, so our exponent on the 1 out of 36, let me fix that up. The 1 out of 36, our exponent here needs to be a 0 because we have 0 successes. And the exponent on the 35 out of 36 needs to be 10 because we have 10 failures. And now we need to find the probability that x is equal to 1. This part right here. So to do that, again, we're going to subtract 10, choose 1, times 1 out of 36. 1 out of 36. And we're going to have 1 success, so that'll be to the exponent 1. And then we'll have 35 failures. Oh, I'm sorry. Yeah, 35, not failures, but the probability of failure is 35 out of 36 still. And we'll have 9 failures because we had 1 success. So I'm out of room, but you can go to your calculator now and figure out this part, figure out this part, and subtract from 1. I also want to talk a little bit about expected value. So I have just enough room here, I think, to talk about expected value. When we look at probability distributions, we talk about the expected value as being the sum of all of the elements in our random variable times the probability of that happening. And we can make a table, find all of the x times the p at x's, add them all up, and so on. Well, it turns out that when you're doing a binomial distribution, there's a little bit of a shortcut. It turns out that the expected value is always equal to the number of trials times the probability of success. So if we were to do that here, in this case, we rolled the dice 10 times. So there are 10 trials times the probability of success. Remember that a success was rolling a pair of double sixes. So the probability of success is 1 out of 36. So we can multiply that and say, hey, 10 times 1 over 36 is the same as 10 divided by 36. So we would expect, if we're going to do 10 rolls, we would expect on average to have about 0.28 double sixes. So not even 1, which makes sense, right? There are 36 different possibilities. We're only rolling 10 times. There's only one way to get a double six. So the expected number of double sixes in this case is 0.28. If we go back just for a second here to the previous example with the allergy medication, in this case we could calculate the expected value as well. So the expected value here is just going to be the number of trials times the probability of success. Well, in this case, there were 10 trials, and the probability of success was 0.7. 10 times 0.7 is 7. So in the long run, you would expect that 7 people would have. Oh, hang on. I was just looking here because my numbers don't seem quite right. Oh no, they're okay. On average, 7 people should expect to have the medication work for them. So that's a quick introduction, well, maybe not so quick introduction to the binomial distribution for probabilities. Again, we could still make a table that shows the distribution. The tables here get a little bit long and cumbersome. Spreadsheets will be handy here to be able to find your distributions, and certainly we could still graph the distribution. So for example, for this example here about the pair of dice, we could actually figure out, if we're going to roll the dice 10 times, we could create our table with all of the possible outcomes. So, whoops, that should be an uppercase P. Let's fix that up. We could still create a table with all of the possible outcomes listed here, well, when we toss 2 dice 10 times, we could have, and remember our expected value is the number of sixes. Well, we could have 1 6, 2 6, 3 6. This is 4 sixes, and so on, all the way up to 10. So this is what I mean about it gets kind of long, and how spreadsheets would be handy here. And then we find the probability that x is equal to x. And so, the probability of getting 1 6 and 2 6 and so on. So we would actually do the calculations that we did over here. This was for getting 2 sets of double sixes. That number would go in here, and we would do another one here. So you can see how a spreadsheet would be really handy here to be able to do those calculations for us. And maybe we'll look at that in another video. And then from here, you could calculate the expected value by finding the sum of the x times the p at x's. So you can go through that and find your expected value just exactly the same way that you would do it for any other type of distribution, for a uniform distribution, or like the ones that we've looked at in the past.